All right, here's a theorem that's used quite a bit when we're dealing with limits. And it says, let c be a real number, and let f of x and g of x essentially be the same thing for all values of x not equal to c. And so we're looking at, they're the same except for at perhaps one point. And it's on an open interval containing c. Okay, so remember we had to have an open interval for limits, for the delta epsilon definition of limits, and it had to contain our c. Okay, so that's where that comes from. If then the limit of g exists as x tends to c, then the limit of f of x also exists and is equal to the limit of g of x. And that's what this says here. So if the limit exists, you know, we don't necessarily have to know the limit, but if the limit exists, then the limit of f also exists and is equal to the same. Okay, and we'll do a couple of examples on this outside of this particular lecture. One of the things, and we kind of talked about this a little bit, but I want to point it back out, is the difference between the undefined, between undefined and indeterminate. Indeterminate is 0 over 0 or 0 raised to the 0 power. Undefined is some number a over 0 where a itself is not equal to 0. Okay, they're fundamentally different in that if you look at the undefined number, that simply means that suppose, and we'll just run a quick example here. Suppose that this actually equaled a real number, and we'll call that real number b. Then that means that if we multiply both sides by 0, that we get a is equal to b times 0, but anything times 0 is 0, and therefore a is equal to 0, and that is against our assumption, and so this is called a proof by contradiction. We assumed something, then show that there's no way it could possibly be that. Okay, and now if we take a look at the fundamental difference here of the indeterminate form, if we assume that 0 over 0 is equal to some value a, then 0 is equal to a times 0, but that's true for all real a. So it's true for all a elements of the real number system. And so there is a fundamental difference between the two. We can certainly work with indeterminates to a point, as you'll learn later on in your calculus careers through a guy named L'Hopital, but we have to be very cautious in how we do that. One of the more important theorems, if I had to guess, I'd say this is one of the most used in proving limits and what they are, is called the Squeeze Theorem. Most of these theorems, there's so many theorems that they don't have names. This one just happens to. All right, the Squeeze Theorem says that if we have three functions, f of h, g of h, and f of x, g of x, and h of x, and they are related to one another this way, where f of x is kind of squished in between the two of them, and that's for all x in some kind of open interval containing c, except perhaps at c, where at c they might be squished together at a single point. If h of x and g of x both have the same limit at c, or as x tends to c, then the limit of f of x also exists no matter what. And as x tends to c, the limit as of f of x tends to L, the same limit shared by h and g. There are a couple of, and before you before you learn about L'Hopital's rule, there is a proof there that shows that cosine of theta is less than or equal to the sine of theta over theta is less than or equal to 1. Okay, well, if you look at the limit as as theta approaches pi over 0 of cosine, well, cosine of 0 is just 1, and so as theta approaches 0, cosine equals 1. As the limit as theta approaches 0 of 1 is equal to 1. And so therefore by the Squeeze theorem, then the sine of theta over theta, the limit as theta approaches 0 is equal to 1. Even though at 0, if you substitute it in, you get 0 over 0. The sine of 0 is 0, theta is 0, and so you get the indeterminate form 0 over 0. It still is equal to 1. And if you graph this on your calculator, you'll see that it'll come in, it'll be moving right along, and it'll all of a sudden get very, very, very thick right near the y-axis. The y-axis, the x-axis is actually up here, and then it'll kind of come off again, and it'll kind of smooth back out. But if you keep zooming in and zooming in and zooming in and zooming in, eventually it's going to cross, and it's going to cross at 1. And so sometimes it's just given to you as just defined to be. And so that being said, they give you 2. They give you the limit as x approaches 0 of sine of x over x is equal to 1. And the limit as x approaches 0 of 1 minus cosine x over x is equal to 0. Okay, now if you think about this, you put this in here for the cosine. If you take 0 and stick it right in there, you get 1 minus 1 is 0 over 0. Wait a minute. Over here, 0 over 0 is 1. Over here, 0 is 0. 0 over 0 is 0. Two different numbers. Hence, the indeterminate form. It's indeterminate because you cannot nail down a number. It's not that it trails off to infinity. It's that it can be literally any number we want it to be.